Good evening, grade 10s. Welcome to video 3 of our chemistry unit this term. We're going to talk about reaction types tonight, specifically the 5 types of reactions we should know. So let's get into it. Here's our learning intention and our success criteria. You can see it's a little bit shorter than our usual ones. But here to learn the 5 different types of reaction and predict products of reaction. And there are 2 success criteria there. So I'll give you a second, fill in your KS table, see what you come up with. Okay then, so if you're still working, give it a pause, otherwise let's go through them. You should know what are your 5 types of reaction. That's going with that describe. If you don't know what it is, it's pretty hard to describe it. And can you do these predictions? And the check-in booklet for the week has a few things on that. So the reason this is important is because if you can use theory to predict an outcome, then sometimes the experiment is not always necessary, or vice versa. If you've got an outcome in mind, you can reverse engineer a process to get that thing as long as you know those proper rules. So this is chemistry is really good on that. If you ever watch YouTube videos on chemistry and people creating stuff in home chemistry labs, all you got to do is know the rules. You start with some basic precursors and you can construct a lot of stuff. So there are 5 types of reactions. Now there is a video on my OneDrive that you can watch to fill in these 2 blanks. Obviously if you go ahead through this video you'll see these as well. So we're going to explain what each of these are as we go through. So if you want to take notes on that, otherwise we'll continue on. So whenever you're looking at writing down a reaction, you've got to know firstly what type it is. You've got to then predict the products. Now when you look at compounds that you've created, you need to look at your valency, your ionic bonding, in order to make sure that they are balanced products, and then you have to balance the equations. Those last 2 steps there, especially step 3, that's a tricky bit, but that's what we did last week with those polyatomic ions. And there's a couple of things you've got to remember. For example, we talk about oxygen or oxygen gas. Well, that's always going to be O2. It's not going to be O on its own. And so those diatomic elements, or those gases like nitrogen, oxygen, hydrogen, chlorine, fluorine, those things are always going to come as diatomic pairs. They're going to come with 2 atoms. The other thing that you need to know are your state symbols. Now, 2 of them are really easy. If it's a solid, you put an S there. If it's a gas, you put a G there. Now, last year we got you started with AQ for aqueous. But this year we want you to actually differentiate between aqueous and liquid. Now, aqueous AQ is for anything that's been dissolved in water. So if you've got, say, a hydrochloric acid, well, it comes from hydrochloric salt, and you can turn it into a solid, so it is something dissolved into water. If you had a copper sulfate solution, well, copper sulfate is a blue powdery solid. You played with it in grade 8 for growing crystals, but we can dissolve it into water and get a solution. Water, however, is always a liquid, so it has been L. If you had nitrogen at a liquid phase, then you again would write L for liquid next to your nitrogen if you were doing a chemical reaction where your nitrogen had to be in a liquid. So anything that is actually a liquid at room temperature, either as a chemical or as a element, or there's not many elements that are liquids, will be given an L. Most of the things we deal with is AQ for aqueous. But always check in, because sometimes these things are not obvious, and you might be like, well, you've only ever seen it as a liquid, but it's actually an aqueous solution. Okay, so let's start with the first. Synthesis reactions. These are nice and easy. Generally, they're going to be elements. Not always. You can get some examples where they're not elements, but generally 2 things come together to make something new. Now, the simple form of writing this is that A plus B gives us AB. Some easy examples: if I take hydrogen gas and I react it with oxygen, normally by setting it on fire, I'll get water. You can see that in the movie The Martian, where he does that reaction. If you have some carbon and you burn it with oxygen, you will get CO2. And that's what happens with charcoal, when you burn it as part of your fire, it creates CO2 gas. And here's a sort of picture to help you sort of see it. A and B, they react together, and now A and B are joined together over there doing the tango. So our first one is synthesis reactions. Now, the opposite of synthesis reactions is, oh, here's an example of it. Potassium plus chlorine gives us potassium chloride. A plus B gives us AB. Notice this one's balanced as well. 2 Ks, a Cl2, so there's 2 chlorines, gives us 2 KCls. Alright, so here's 3 examples. I'm going to do the first couple, and then I want you to do the last one. So sodium metal, well, sodium means it's Na, plus chlorine gas, Cl. Now it's a gas, and chlorine in this case will come as Cl2. And that's going to create something. Now we said this is a synthesis, so they're going to just combine Na, Cl, but we've got to check the valency. Now sodium, remember, is +1 all the way over on the left hand side. Chlorine, -1 over on the right hand side. They balance, we don't need to do anything here. Okay, so this compound is balanced. This formula is not balanced because I have 2 chlorines here, but only 1 chlorine there. So if I've got 2 chlorines here, I need to slap a 2 out the front. But now, I've got 2 chlorines, that's good. But I've got 2 sodiums, 1 sodium. So I'm going to need a slot of 2 there at the front as well. Okay. Now the second one, we're going to have to do a couple of steps on this. So solid magnesium. Magnesium's a metal, so we're just going to write the metal, Mg. Fluorine gas. So fluorine is F. That's a gas, and it's right above chlorine. So you might clue that's going to be F2. And it's going to make, well, it's a synthesis. A plus B gives us AB, MgF. Now let's think about those elements and where they are. So magnesium is in column 2 of your periodic table. It's an alkaline earth metal. That means it's a 2+. Fluorine, those in column 17, or 7A, depending on how your periodic table is labelled. It's a halogen gas. That means it's 1-. If I have a +2, and a 1-, they don't balance. I need another 1-. So it's not going to be F, it's going to be F2. So in this example, we had to balance the compound. Now we can go and balance the equation. But the good thing is you can say, oh yeah, 1 Mg, 2 Fs, sweet. That's all done. So those ones are okay. Last one, aluminium metal. Okay, well, aluminium, Al, plus fluorine gas, which we've established as F2, gives us AlF. But again, we need to balance the compound. Aluminium is a +3. It's in either column 13 or it's in column 3A, depending on how your periodic table is labelled. It's over in that right hand box underneath boron for the B. It doesn't have a nice easy name to remember in terms of the type of metal, but it does come, it's in part of the simple metal group. But the fluorine, remember, was that -1. Well, that's problematic. So in order to balance off that +3, we're going to need 3 of these. Now we need to go and balance our formula, because we've balanced the compound. This is okay, but aluminiums match, but fluorines don't match. Now I'm going to skip forward the math a little bit quickly here, because this is a 3 and this is a 2. There's no common multiples. The lowest common multiple. Sorry, there's no common denominators, but the lowest common multiple between these two is 6. So I'm going to need a 3 here. 3 times 2 would be 6. I'm going to need a 2 here. 2 times 3 would be 6. So now my fluorines balance, but my aluminiums do not balance. I've got 2 aluminiums, I'm going to need a 2 here. So in each of these, we showed a couple of different steps. Firstly, we always had to identify our reactants. We had to predict our products by understanding this rule of synthesis reactions. This one here was balanced, the compound was balanced, but the formula was not. This one here, the compound wasn't balanced, but the formula was after we balanced the compound. And this one here, neither of them were balanced. We had to do both steps. You always have to balance the compounds first, then you can go and balance the formulas. If your compounds are wrong, you won't be able to do it at all. So, let's move on. Oh, it was actually there written underneath it. I forgot all about that. Let's just skip forward. So, our second one is called decomposition. Okay, so the opposite of a synthesis is a decomposition. Decomposition just means to break something apart, where we have one reactant and it breaks into two products. It basically looks like AB becomes A plus B, or in this picture down here, BC becomes B plus C. It's the opposite of our two dancers coming together. And here we go, oh, maybe these two are dancers dancing, and then they go their separate ways. Some easy examples, the opposite of the one we saw before. If you take water and you run a bit of electricity through it, it breaks up into hydrogen and oxygen. You may have seen that in the class in grade 8. Another one there, mercury oxide, if you heat it up, will break apart into mercury metal, and the liquid silvery stuff you've seen, and oxygen gas. I think I have a picture of that. Yeah, so here we have mercury oxide. It's kind of a yellow, brownish, orange colour. Heat it up, looks a bit weird, and there's the pure mercury left over and the oxygen gas that's bubbling up the side. Okay, so we've taken HGO and split it up into our two pieces. Let's have a look at some examples. Write and balance the following decomposition. So in this case I've given you the actual thing we start with, because I'm not getting you to learn how to write chemical compounds from names. You'll do that in Year 11 or 12 chemistry. However, you should be able to go, well, if I start with this, what could it turn into? So here we have potassium chlorate. K, potassium, Cl, filter chlorine, and O2 to turn the chlorine into a chlorate. We want to turn it into two things, a salt and a gas. So if we have a look here, we're going to ask, well, what gases could we think? We could have chlorine gas, or we could have oxygen gas, because we can see some oxygen there. Now, this word salt means a very important thing in chemistry anyway. A salt is anything that is a metal that is reacted with a halogen. Anything in that column 17. Fluorine, chlorine, bromine, iodine, all the ene elements over there. So that means my salt is going to have to be KCl. Now, some of these rules you're not expected to know. Okay? However, anything we tell you to decompose, you're going to have to be able to do for yourself. So the gas in this case is going to be oxygen. This won't be O, it'll be O2. Oops. And we can see in this case that it's actually balanced off. KCl, well, O2 is fine. KCl, well, K is +1 and Cl is -1, so those things will balance, and our entire formula balances as well. Okay. Lead carbonate turning into a powder and a gas. There's lots of powders that could be there. You could have lead carbonyl. I don't know if that's going to be a powder or it might be an organic compound of some sort. But in terms of gas, the gas that stands out to me here would be CO2. Okay, because that would leave behind one oxygen, and any metal with a bit of oxygen is basically some sort of rusted powdery thing. So this is going to turn into lead oxide plus CO2. And you might go, well, how do we know that it's going to be lead oxide in that formula? And the thing is, we don't, and as I've said, we are ignoring the transition metals. So we're not going to even touch that with the 10-foot pole. Okay? So anything that has to do with any valency or ionic bonding with metals in the transition metals, okay, you would get given what their valency is. what their charge would be. If it's something that is in column 1, column 2, column 13, 14, we'd expect you to use your periodic table and work it out because we've taught you those rules. But those ones in the middle, lead being one of those ones in the middle, we're not worried about it. So for this one, lead oxide looks to be fine to me. Let's move on. These are the ones that start getting a little bit more complicated. Single replacement reactions are where one element, or a compound, because you can have a compound, kicks part of a larger compound out and takes its place. And there are two forms. If you have A plus BC, if A is a metal, it's going to kick B out and take its place. And so here we've got AC plus B. If A is not a metal, it's going to kick C out, take its place, and so you'll have BA plus C. And the thing that you have to remember is that when you have any sort of compound written, the metal always comes first. So if you have a metal coming in, you kick the metal out. If you have a non-metal coming in, you kick the non-metal out. In terms of a picture, you can think of it like this. Here we've got this dude, rich people dancing. He comes in, kicks him out, starts dancing with the girl. So in this case, it's kicking one person out and taking their place. But it has to be the same person, otherwise it doesn't work. As an example, here's lithium plus water. You've seen sodium plus water last year, and that's an example of a single displacement reaction. The lithium comes in, the lithium comes in, kicks out one of the hydrogens, and then takes its place. So you get some hydrogen left over, but you've got lithium hooking up with half the water, the hydroxide in this case, to make lithium hydroxide. So let's have a look at some examples. Here's one single replacement. Zinc metal reacts with aqueous hydrochloric acid. So let's write down those two things. We have zinc. Just trying to remember where I put the order thing that's going to fill in a second. We'll just do it here. Zinc, all on its own, plus hydrochloric acid. Okay, so zinc is a metal. It's the positive thing. Hydrochloric acid, well, the H in this case is the positive part, so the zinc, just drop my pen, the zinc is going to kick out the, sorry, trying to find my pen there, there it is, the hydrogen, because it's going to take its place. Zinc is positive, hydrogen is positive. So that means our reactant is going to look something like, weird. Let's do a slightly better arrow there, guys. It's going to be a zinc combining with a chlorine, okay, and there's going to be some hydrogen left over. Now, hydrogen, remember, is a diatomic gas. It's one of those gaseous elements. So hydrogen is going to form H2. But now we're going to think about this zinc chloride. How's that going to look? So, seems to be having a bit of a hissy fit there. So, zinc chloride, zinc is a +2. It is a transition metal, so we would tell you that on an exam. But chlorine, remember, is a halogen, so it's a -1. So if that's +2 and that's -1, we're going to need a 2 here. And now we can start thinking about balancing. So we've got one zinc, that's good. One hydrogen, 2 hydrogens. Okay, so we're going to need some more hydrogens. Let's slap a 2 here. This thing is just randomly drawing. 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. So that balances off now. And if I pop up the one that I have thing, almost got it perfect. You see the zinc. My pen is being silly. Apologies. We can see here the zinc plus the hydrochloric acid gives us zinc chloride plus H2. Okay, the zinc kicks out the hydrogen cation. So anything that's positive, remember, is called a cation. Maybe this doesn't work for you, but you can consider it, well, cats are fun pets to have around. It's a positive, so cation is the positive. Anion kind of sounds like onion, And you just got to replace the A at the front with an O. And onions are negative things because they make you cry. Because no one likes sulfur molecules. Now this is the tricky one. Double replacement reactions. Double replacement is when you have two compounds swapping partners. So the positive of one kicks out the positive of the other, but so the positive of compound 1 kicks out the positive from compound 2, but the positive from compound 2 goes to where compound 1 was. It's like if you imagine two pairs of best friends sitting there talking in class, and the teacher makes two of those people stand up and swap, so now two people who don't like each other are sitting next to each other. That's a double replacement reaction. Okay? Now, one way to visualize it, here I've got a penguin with a tuxedo hat and a pig with a pair of glasses. Well, they're going to swap their ornaments, so now the penguin has the glasses and the pig has the tuxedo hat. This is a double replacement reaction. Sometimes it's called a double displacement reaction as well. So here's a couple of examples, and I think I've got some practice ones in a second. I treat this as a pattern matching, kind of like if you've done binomial expansion mathematics, you might have been taught about the acronym FOIL. Okay, first, outer, inner, then last. So now, if we treat the same thing here for our silver and our silver nitrate and our sodium chloride, well, here's our first, the Ag and the Na, and here's our last, the NO3 and the Cls. So the Ag is going to kick out this Na, and the Na come back to being in the NO. So here the Ag and the chlorine, well, they've hooked up our outers, and here the NO3 and the Na, well, they've hooked up over here as well. Same thing down here. Potassium and sulfur, barium and nitrogen, well, the potassium's hooked up with the nitrate, and the barium's hooked up with the sulfate. Okay? But you've got to be careful with this. If you write your formula incorrectly, you won't have the right pairing. You have to have it written with the metals first and the non-metal part second, so that you can just pattern match it. So if I put on my thing, you can see here, I've taken, problem for having old devices. Our first one here, the silver, and the last have joined together. Okay, and what's left over has become the second one. Let's have a look at some examples. So here is one sodium carbonate. You might have this in your home as baking soda, and it reacts with hydrochloric acid. Oops. So here's our starting part, Na2CO3 reacting with HCl. So my good pen, here's our positive bit, here's our positive bit, okay, and so our Na, okay, will hook up with the, my pen's very silly, the Cl. So let's rub that out. With the Cl, okay, and that means the hydrogen here, our H, has to be hooking up with our CO3 over there. H and then CO3. Alright, now messy handwriting aside, unfortunately I can't quite fix this pen quickly right now, so I'm going to have to deal with that later. We need to balance our compounds. So we have here Na, which is a alkali metal, +1. We have chlorine, that's a halogen, -1, so that's okay. But here we've got hydrogen, which is +1 because it's in that first column. We've got our CO3, our carbonate molecule, which we learnt last week was -2. So we're going to need an extra hydrogen there to balance off the carbonate. Okay, Now we can go back and balance our formulas because we have 2 sodiums here but only 1 over here. So let's slap a 2 there out the front. So 2 sodiums. Okay, that's good. But now we've got 2 chlorines but only 1 chlorine here. We've also got 2 hydrogens but only 1 hydrogen here. So if we slap a 2 there, I'm so sorry about this, then we now have our balanced formula that our NaCO3 is going to react with 2 hydrochloric acids to get 2 NaCl and H2CO3, which would balance off. And that's what's underneath my messy handwriting. So I'm going to erase all that working just so that we can actually see it neatly. Okay. And so now we can see we've got our 2 NaCls, and they are balancing off against what we've got over here on the left. We've got our H2CO3 over there on the right as well. Now our last reaction type is combustion reaction. Now combustion reactions are very straightforward in that at this stage they're sometimes called redox reactions, but redox reactions have a little bit more complications behind them, so we're just going to get you started with combustion reactions this year. Combustion is any reaction with oxygen that produces some sort of oxidized, that means combined with oxygen, that's what oxidized means, product. Most of the time it's going to be a hydrocarbon, especially at this stage. And so the product is carbon dioxide plus water. You saw a really basic example of this in the last couple of years when we talked about photosynthesis, where if you take sugar, C6H12O6, and you burn it with oxygen, you will get some combination of CO2 and H2O. The fuels could be very small things like methane gas, CH4, ethane gas, C2H6, or some very, very long hydrocarbons like the ones we have in our cars, which are significantly longer, and so they produce more carbon. But it'll always produce just CO2 and H2O. Right? This is the last one. I don't have any examples of this because this is very straightforward, and as long as you follow this rule, whatever fuel we give you plus oxygen will give H2O and CO2, you'll be fine. So we'll finish off there for the night. Thank you very much for listening. Have a great evening, and we'll see you guys soon. Bye.